Bifrost is a procedural framework that can create simulated liquid effects quickly and easily. It also allows you to use gravity and collision objects to affect the simulation, creating splashes, pressured flow, and other related effects. In this series, we'll create a basic still water simulation, then add wave motions to it, and ultimately finish off with a more dramatic tidal wave. Make sure to set the current project to the provided scene folder, then open the file Coastal Town Part 1 Start. This scene contains a small coastal town built at a 1/100th scale, where 1 unit equals 1 centimeter. As you can see, the coastal pier stretches out into a container object, representing the ocean that we'll simulate. But in order to create a liquid using Bifrost, we need an object to emit the liquid from. Create a new polygon cube and rename it Ocean Emitter Geo. Position it at the center of the container and scale it so it roughly fits inside. This scale ensures that our ocean will get filled quickly. In the attribute editor, set subdivision's width to 5. Use the extra edges to conform the shape of the cube a little better to the seabed, so the water will settle a little faster once we start simulating. With the emitter selected, go to Bifrost, Create Liquid. Maya creates a Bifrost liquid simulation within the volume of the emitter object, along with 3 new nodes, a Bifrost container node, and corresponding liquid and mesh nodes. The container node represents the data generated by Bifrost. The liquid node is the simulation's shape node, which displays Bifrost data to the user. The mesh node is empty for now, but is set up to receive meshing information when Bifrost meshing is enabled, which we will demonstrate later. Before we play through the simulation, go to the animation preferences and make sure that playback speed is set to play every frame, and max playback speed is set to free. This is an important setting for most dynamic effects, because computing each frame depends on the state of the frame before it. Also, we don't want Maya to constrain the playback speed at this point by imposing a specific FPS. Select the Bifrost 1 node so we can track the simulation's progress, then rewind and play through the simulation. Maya begins filling the scratch cache, a temporary cache designed for quick iterations. Green denotes the frames of the cache that have already been processed, while yellow denotes frames yet to be processed. Note that the simulation is computed outside of Maya by Bifrost, which means you can scrub through the processed frames and continue to work even as Maya builds the cache. By default, Bifrost uses particles to represent the density of our liquid, but they're currently rather minuscule. Select the Bifrost node, and in the attribute editor, go to the Bifrost Shape tab. Here you'll find controls to affect the particles display in the workspace without impacting the simulation. In the particle display section, increase point size to 3. While you're at it, hide the emitter to get an even better look at the particles. At any time, you can also turn on the Bifrost HUD to see exactly how many particles are in your scene. As you scrub through the scene, notice how the liquid particles fall very slowly right through our seabed. This is because the simulation is not set up for our current scene scale. Recall that we're using a scale of 1 unit to 1 centimeter. However, Bifrost is set up to work at a scale of 1 unit to 1 meter. To get an accurate simulation, we'll need to account for this. Select the Bifrost object and go to the Bifrost Liquid Container tab in the Attribute Editor. The Liquid Solver attribute's Gravity Magnitude attribute determines the effect of gravity on the liquid. The default value of 9.8 is too low at this scale. Since there are 100 centimeters per meter, we need to amplify this gravity 100 times to get an accurate effect. Similarly, select the emitter object. In its Shape tab, under the Bifrost Liquid Emission Physical Attributes section, notice that density is set to 1,000 kilograms per unit cubed. To express the equivalent of this in centimeters, we need to divide this by 100 cubed, or 1 million, which leaves us with 0.001. Also, in the Bifrost Liquid Emission section, turn off continuous emission, since we want a finite-sized body of water. Finally, the liquid particles fall straight through the container because Bifrost doesn't yet know of its existence. Select both the Bifrost node and the Ocean Container Geo object. Go to Bifrost, Add Collider. Maya adds a new Bifrost section to the Container Object's Shape node, matching its collider state. Play the scene again. Maya generates a new scratch cache to reflect all the changed settings. However, notice that the particles now seem to float above the container in a strange fashion. In the collider's new Bifrost Collision section, set mode to shell. This informs Maya that we want the liquid simulation to collide with a thin shell around the faces of our container, rather than with the entire volume of the virtual solid it creates. Rewind and play the simulation again to regenerate the scratch cache. This time, most of the water particles fall into the container, but some of them manage to escape. This leak happens due to the partial lack of collision detection between the particles and the container, calculated on each simulation frame. One way to prevent this is to increase the collider's thickness value to, say, 2.6. This thickens the voxel width of the collision area to close up holes relative to the particles. In this specific case, this change is enough to fix the problem. In other cases, you might need to also increase the amount of simulation calculations per frame, or transport steps per frame, using the Bifrost Liquid Container node's emission controls. This can lead to more accurate solving, but at the cost of computation time. Rewind and play the simulation again. This time the particles land in the container and splash around before settling. You can now hide the container to give us a nice view of the liquid. Thus far, we've been making heavy use of the Bifrost scratch cache. The scratch cache is stored in your system RAM. You can manually specify the maximum amount of RAM your scratch cache can occupy in the Bifrost options. To ensure your system remains responsive at all times while using Bifrost, we recommend setting this to a value lower than your maximum system RAM. Also notice the coloration of the particles, ranging from dark blue to white. This gradient actually has nothing to do with our final rendered look. It is a diagnostic tool for measuring various attributes of our simulation. In the Attribute Editor, go to the Bifrost node's Shape node. In the Particle Display section, you can see that Maya uses colors to visualize the velocity of each particle. Expand the Color Channel Remap section. The color ramp shows particles ranging from dark blue to white, depending on how fast each individual particle is moving. Let's reduce the value range from 0 to 10 units, since none of the particles are moving particularly fast. Now you can get a much better visual sense of the particle speed without having to run our simulation in real time. Alternatively, you can choose to have this color ramp represent a number of other metrics. The particles we've simulated so far give us a good preview of the liquid's flow, but they aren't the only Bifrost display method in the workspace. Under the Display section, you can also toggle the voxel part of the simulation. Voxels represent the grid values in 3D space that Bifrost uses to calculate particle locations. Voxels give you a much fuller sense of the simulated liquid. Like the particles, You can use the voxel's color channel remap controls to highlight complementary information about your simulation. If you render the scene in Mental Ray when either particles or voxels are enabled, Maya renders an isosurface representation of the voxels. This allows for a quick render in Mental Ray. However, for the best quality, you'll want to render the liquid mesh itself, not the voxels used to create it. In order to create the most accurate rendition of your liquid, enable the Bifrost meshing controls from the Bifrost Shape tab instead. This creates the polygonal liquid mesh generated by Bifrost and stores it in the Bifrost mesh object. This mesh is connected to a Bifrost liquid material shader rather than a diagnostic coloration. This is the same shader that Maya uses to render the voxels. Before rendering, make sure to hide the Bifrost object so you don't render the mesh and the isosurface over top of each other. Try rendering again to see the difference. While both versions share the same shader, you can see a marked improvement in the fidelity of the mesh render. At the moment, the shader color is a little too uniform. We can take care of this by adjusting the shader attributes in the Bifrost Liquid Material tab. First, take note of the diffuse and diffuse remap sections. Right now, the primary diffuse color is being overwritten by the blue to teal remapping. However, the range is so high that only the lowest end really applies anyway. We'd actually prefer a more uniform tone, so you can disable the color remap and just use the main diffuse color. More importantly, in real life we'd expect some white foam in the water based on the churning beneath the surface along with loose sediment. Scroll down to the foam remap section. Foam is an additive layer on top of the material's diffuse layer that depends heavily on the liquid's vorticity, representing its churn. Here, the foam's color and weight are mapped to ramps linked to a value range. Right now, this range's input min and max values are much too high to really have any effect in our scene. Let's lower them to 0 and 30 respectively. Additionally, let's add a new point to the lower end of our gradient, then change the color to gray to mimic loose sediment at the bottom of the water. And we'll adjust the foam weight ramp to create a small peak to exaggerate the foam's density effect a bit. Render the scene again. Maya generates patches of white foam beneath the surface. This is a pretty good start to our contained ocean simulation. However, the water itself isn't very interesting once it settles. In the next movie, we'll spice up the simulation by introducing some waves.